Hey, Red Devil scholars and chemistry genius. This is Coach Scott. We're going to talk about quantum numbers, the secret of the universe. And it's amazing that when you see what they are, you're going to be like, huh? Okay. So if I get that to move, let's get this to move. All right. So, we've already talked about in the previous video. There are four quantum numbers. And the quantum state of the electron is specified by the four quantum numbers. No two electrons can have the same set of quantum numbers. Just like every one of you have a different house address or street address, every electron has a different address in the atom. And this is where the quantum numbers come from. So we've got the principal quantum number, and that's the first one, and it's designated by the energy shell. And that's going to be a whole number greater than or equal to 1. So it's going to be 1, 2, 3, 4, 5, 6, or 7. Right now, we only have 7 principal quantum numbers. The angular quantum number designates the orbital shape. S is 0, P is 1, D is 2, F is 3. All right? So, those would be 0, 1, 2, n minus 1, right? Or the L number. Okay? 0, 1, 2, n minus 1. The magnetic quantum number designates the orbital rotation. So that's going to be minus L is greater than or equal to the ML number, or L greater than or equal to the ML number. We'll work through these, and I've got charts that I'll give you to help you understand those. The spin quantum number, ML, will only be plus 1/2 or minus 1/2. And from these numbers, we can get the address of each and every electron that's in an atom. Okay? Because all of them have to be unique. I don't know what just happened there, but something weird happened. We went red. Okay. So now we can know where these addresses are. So, there's some combination of quantum numbers that are impossible because of the energy levels. If n is 1, an electron can only be in the s subshell. So a quantum number for n1 would be 1, comma, 1, comma, 1, comma, plus 1/2 or minus 1/2. So there's two addresses for anything in the first n. Now n2, an electron can only occupy an s or a p subshell. When n equals 3, an electron can only occupy s, p, or d subshells. If n equals 4, the electron can occupy either the s, p, d, or f subshell. Okay. Now, orbitals will have the same value of n, will form a shell. Now, there can be different orbital types within a shell. The different orbital types within a shell are called subshells. So, N1, you can only have one S, you can only have one orbital, the S orbital, and the total number of orbitals for N1 is 1. So you can only have 2 electrons in each orbital. You've only got one orbital, so N1 can only have 2 electrons. Now N2. N2 can have a 2s orbital subshell, or it can have a 2p subshell. Now there's only one orbital in the 2s, or in the s's. There's 3 possible orbitals in the 2p subshell. All right. So if I add 1 plus 3, I get 4 total orbitals. And each of those orbitals can have 2 electrons. 4 times 2, because for the 2 electrons, I can have 8 electrons in the second energy level. Now, energy level 3, I can have 3 possible subshell types. I can have the 3s, the 3p, or the 3d, and the 3d rather. So, the 3s can have 1 orbital in it. The 3p can have 3 orbitals in it. And of course, the 3d can have 5. So if I add that up, 1 plus 3 plus 5, that's going to equal 9. So that tells me in the third energy level, I can have 9 total orbitals. That means I can have 2 in each of those orbitals, 2 electrons, so I can have 18 electrons. You might be seeing a pattern here from 9th grade or 8th grade science. The fourth energy level, all right? You can have 4 different types of subshells. The S, the P, the D, and the F. The S can only have 1 orbital. The P can have 3, the D can have 5, the F can have 7. If I add all those up, that gives me 16 total orbitals. Well, you can have 2 electrons in each of those orbitals, so you can have a total of 32 electrons in the fourth energy level. Again, we're all building on top of it. So let's do a quick check. If n equals 1, an electron can occupy which of the subshells? The 1s, the 2s, the 2p, or the 3s? Now, if you go back to our chart, the N1L, the 1N can only have 1 subshell, the 1S, so of course that's going to be A. If you don't believe me, there you go, A. Easy peasy. N equals 1. That means it can hold a maximum of how many electrons in the first energy level? We'll pause and come back, and of course it's going to be 2 electrons because they have to have opposite spins. What's the maximum number of electrons that can occupy the N4 shell? Pause. Well, I can draw this out. Let's hope I can. Oh, I got to turn off my little blue thing. So I'll do that real quick. All right. So I'm going to write this down because I don't have my chart with me, say. So the N4, the 4 energy level, I can have an S, P, D, maybe D or F. And of course I can have 1 in the S, 3, I can have 3 different p orbitals, I can have 5 d orbitals. Turn that off and see if we can turn it back on. It's not letting me write. I can have 5 there and 7 in the F. All right, so I've got 1, 3, 5, 7. 7 and 5 is 12. 12 and 4 is 16. I can have 2 electrons in each of those orbitals. I've got 16 total orbitals, so that means I can have D. I don't know why that's doing that, but it is. So we're not going to worry about it. So the answer for that would be D, or 32. Go back and turn my blue cursor on. 32 electrons. Okay. An electron is in the 6F state. So what's the principal quantum number? Pause. And of course, the answer to that, well, that is really weird. Yeah, it's not doing right. That, of course, is going to be A. The 6 is the end of that subshell, of that orbital. So, as the number of electrons increases, so does the repulsion between them. You're getting more electrons. They're all the negative things. They don't like each other. So complex atoms contain more than one electron. So the interaction between these electrons have got to be accounted for in their energy levels. So this means that the energy level, the energy depends on both the N, the subshell, or the shell rather, and the L number, the subshell. So the energy level, all right, the shell and the subshell are the type of shape. So some of these sublevels on a given N may have less energy than sublevels on a lower N level. So look, my energy goes, this is the lowest energy, 1s. Then I'm going to go to 2s. That's got a little bit less energy, or more energy than 1s. Then I've got my 2p orbitals. Then I'm going to the nth level. So my 3s, that's got more energy than the 2p. The 3p, that's got more energy than 3s. But notice that 4s has got less energy than the 3d. Let's see if you can think about it. Why is that? How many electrons are in the, how many subshells are in the 3D level? That might have a little something to do with it. And there's some other things. It's pretty complex. But it's good to know this chart, or know how to use the chart. Let's put it that way. So the energy of an orbital depends on what? Pause. If you said the N level and the L subshells, you'd be correct. So that would be B. This is a good one. Which of the following correctly sequences the orbitals in order of increasing energy? Well, 1s is the first of all those. Then it goes down to 2s, 2p. Now we got it. Ooh, it cannot be C because there's no such thing as a 2D orbital. So then we got 3s, 3s, 3s. That's cool. Then we've got a 3p. We got back to that chart. That's right. All right, so 3s, C's off, 3p, 3p, 4s. Well, that's not true. Okay, 3D. So it's going to be 3p after the 3s. Now, if you recall, the 4s actually had less energy than the 3d, so the answer to this is B. Whoops. An electron is in the 6d state. How many electrons are allowed in this state? So, how many d orbitals are there in the d's? I'll pause. And you should have said 5. So there's 2 electrons in each of those subshells. So